everyone. Is there anyone in this room who does not speak Portuguese? Please let me know. Okay.
Okay, good.
English, okay.
Okay, great.
Okay, it's my great pleasure to introduce our colloquium speaker today, Professor George Matsas, who is known for most of us here. George did his PhD here in the IFT. At the time, it was close to Paulista Avenue in 1991. And then he did a bunch of postdocs in Chicago, USP, IFT again. He has been a professor here since 1995. His main themes of research are general relativity and QFT in curved space-time. And he has received many prizes over the years, including the Outstanding Referee from my APS. He's a fellow of the São Paulo Academy of Sciences, and also received many prizes regarding supervision of students, which is something very interesting to see. Okay, thank you very much, George, and the floor is yours.
Thank you very much for the introduction, and thank you very much for the invitation. It's always good to speak back home. And today I would like to deliver to you a seminar entitled The Gravitational Self-Decoherence Model and a Gentle Recovery of the Classical World. This was done in collaboration with my PhD student, Gabriel Aguiar, who did all the hard work and shared with me all the responsibility about the conceptual issues of this work. And what's this seminar all about? It's about the following. So considering that macroscopic bodies consist of quantum blocks, as we know, the reductionist law posits that the classical world should arise from quantum mechanics. So I bought this idea for long. And I think that this viewpoint is legitimate as long as it does not offend the background space-time. And so what I would like to claim is that it does. It does offend in some regimes where we believe that quantum mechanics should not be trustable. So the outline of the seminar is the following. In the first part, we present a kind of manifesto for imposing a Heisenberg cut in quantum mechanics, basically defining what's the domain of validity of quantum mechanics. And the second part, once you agree with that, if you don't, well, the second part is useless. If I convince you of the first part, so we have to do something to forecast what kind of new physics would be expected at this Heisenberg cut, which is going to be at the Planck scale. And what we present is what I believe to be the simplest gravitational self-decoherence model that would predict what is the new physics at the Heisenberg cut. Okay, so in order to make our case, I have to go back to space-time theory and wonder or ask what is the minimum number of standards you need in order to define a space-time. This is not usually discussed when we have relativity in usual courses. I have to do it here. So we know that all observables in nature can be expressed in terms of the standards defined by the international system. And the international system has set 7 basic units. So if you have the 7 basic units, it's for sure enough in order to express all observables of physics. The fact is that the 7 basic units of the international system, they are not independent from each other. So although they are sufficient, they are not necessary. The next point that I would like to recall you is that the international system was built over the MKS system, which has 3 basic units, meaning that with 3 basic units, meters, kilograms, and seconds, these basic standards, you are, if you are endowed with these three basic standards, you are able to express all observables in nature. Please interrupt me anytime if you have any doubt, okay? Okay, the question now is whether, although they are sufficient, whether they are necessary. And again, the answer is no. Let me try to convince you that we don't have to produce mass standards and deliver all over the laboratories in order to allow different experimentalists to make their predictions, say, about the electric charge and compare the results among each other. First of all, I would like to recall that the kilogram standard was introduced 70 years after Newton's death, and only because of commercial reasons during the French Revolution. And it was just a matter of trading, right? So there were people used it to cheat, and they decided to make a standard and deliver to people in order to avoid traders to cheat when they made their transactions. Indeed, this is a common knowledge. Meaning that no prediction by Newton or by anybody after him needs this standard that we have defined and used to call as kilogram. And this is a common knowledge that was lost for some reason. I don't know why. So let's see what Maxwell writes 150 years later, Newton's death. He writes that mass, this is in the preliminaries of his masterpiece, a treatise of electromagnetism and electricity and magnetism. And in the preliminaries, you can read that mass is defined with respect to its attractive power, and the dimensions of mass are distance to the third power over time to the second power. And this is precisely these units that Newton used in order to express mass. He didn't know anything about kilograms. Why? Because if you want to know the attractive power of Earth, say, what you must do is to set some test particle at some distance r, that of course is measured with rulers, and then measure what's the acceleration that this test mass drops towards the Earth, and acceleration again you measure with rulers and clocks. So when you put these two things together, you have what's the attractive power of Earth, which is its mass. The conversion factor between this useless unit, kilogram, and these units that was used by Newton, Maxwell, and all people at that time to express mass, namely the conversion factor is what we know these days by G, the gravitational constant, was introduced 150 years after Newton's death. In 1873, precisely the same year that Maxwell wrote what he wrote here. Okay? And G is very convenient because 1 kilogram corresponds to this massy quantity in terms of time to the third power, distance to the third power over seconds to the second power. Okay, so indeed, if you don't use, as Newton did, because he didn't know anything about kilograms, if you don't introduce this gravitational constant, so G is equal to 1, you don't have, Newton introduced it, you have G equal to 1, and Newton introduced his gravitational law in terms as if G were 1. So all these tell you that we don't need this kilogram that is kept in Paris in order to make our measurements. Okay? Rulers and time, clocks are enough. Okay, so I hope I convinced you that we can measure mass in terms with rulers and clocks, and the question now is whether or not we do need, they are sufficient, but are they necessary in order to express all observables in nature? And the answer is no, they are not if you define these observables in relativistic spacetimes. In relativistic spacetimes, you can dispense meters and stay only with clocks. Let me try to convince you of that. So I think the easiest way is what I'm going to do here. There are different ways to convince you of that. But if what I'm saying is true, I should be able to measure the size of a ruler, right, like this, with clocks, only with clocks. And the procedure is the following. Take 3 clocks to measure this rod here, okay? The first one stays at the left-hand side, still. Then you kick 1 second clock to the right, and this clock is, the protocol is that this clock is going to go to this direction freely, and it's going to measure the proper time to go from the left-hand side to the right-hand side. Then when it arrives here, the right-hand side, you kick back another clock that takes some other time because there is no standard of kicks, so it can take any time, T2. And the third clock, the clock number 3 that stayed here at the left-hand side, just measures the round trip of clock 1 going to the right and the clock 2 going back to the left. No matter what they are going to measure, if they are in a relativistic space-time, you put everything together here and you get the same distance in light seconds. Meaning that you don't need any standard and a ruler a standard ruler in order to measure, say, what's the size of this rod. You can only use clocks. This equation does not hold in Galilean space-time, because in Galilean space-time you need 2 different standards, meters and clocks, in order to express your observables. Yeah?
Suppose the speed of light depended on time. Suppose in 1,000 years, the speed of light was different than it is today.
Then you are not in a relativistic space-time.
Okay, so then, but then using your units, you can't do it. You can't describe
No.
right?
I'm not using my units. The claim is that if you are in a relativistic space-time, you only need one standard, meaning clocks, in order to define it and to test it.
I
now, if you make for example, if you test this equation and this equation does not hold, then you are not in a relativistic space-time and you have to change everything.
Okay.
For example, you are in Galilean space-time, and then in Galilean space-time, the speed of light could vary, and in Galilean space-time, the conclusions change, and you would need 2 standards. Okay, but still, let me just emphasize that there are some people that claim that you don't need any standard, for example, Michael Duff, and this is meaningless in the sense that suppose that you are in a space-time with a black hole, and you want to measure the size of this black hole. You need at least one standard in order to make the size of this black hole, meaning the area of this black hole, and you can make it with clocks. You need one standard. One standard is necessary and sufficient in order to define a relativistic space-time and to test a relativistic space-time. This is just, plain space-time theory. Okay. So I'm going to make a kind of feng shui here in the sense that because all these quantities here are conversion factors, I'm going to make all of them equal to 1, differently from the Planck constant, because the Planck constant gives a physical quantity that is the angular momentum of elementary particles. They have a completely different status from these quantities. Okay. For example, in natural units, just to make sure this point is very simple, that I use, we usually make h bar equal to 1. But in order to make h bar equal to 1, you have to test in advance whether or not this constant, the angular momentum of particles, if whether or not this constant is constant, right? This quantity is constant. You need to do so, you need clocks, and these clocks, with these bona fide clocks that I'm going to define next, if you conclude that h bar is constant, then, and only then, after this step, you can redefine your quantities and make everything dimensionless. In other words, if you make physics as we know, you need standards in order to measure your quantities. Okay, but now the question is, what are bona fide clocks? What are bona fide, right? What a apparatus that measure time must satisfy in order to be considered a bona fide apparatus. And you can again ask to our space-time theories, because the answer is there. Okay, so the definition is the following. Take any two events arbitrarily close to each other. If you're, in order to bona fide clocks, so this is very important that they are arbitrarily close and causally connected. Bona fide clocks must satisfy the following condition. Independently of the past history and state of motion between these two events, it doesn't matter whether the clock is or not accelerated between these two events, they must ascribe the same real number to the time interval between these events. This is necessary and sufficient condition for a clock to be a bona fide clock. So every time we make any prediction about time, we are assuming the existence of these clocks. And indeed, atomic clocks satisfy in very good approximation this condition. Yeah?
But those agree then only if they are both in geodesic motion?
No, no, not at all. This is why they have to be independently of the past history. I mean, the time interval between these events, right? So if I make like this, my clocks, if they begin, say, suppose that they begin with 0 and 0, and I make like that, one can arrive here with 10 seconds, in 5 seconds, but the important thing is the time interval between these two arbitrarily close, causally connected events.
Yeah, but that is not true. I mean, we know.
No, this is true. This is true. The time interval between this P1 and P2, independently whether it arrives here 10 seconds, from this to this, if it takes 10.0015, this one is going to arrive here at 5, and then between this event and this event, it's going to take 5.0015. The time interval is the same.
No, I'm very confused because, you know, the geodesic is the minimum proper time. So each of the clock is measuring proper time on each trajectory.
It doesn't matter. I mean, the time interval between P1 and P2, it doesn't matter whether, look.
They are connected by a time-like curve, right? So there is only one time-like curve that gives the geodesic.
Suppose that they measure here 0 and 0 here. This is not geodesic, this is not geodesic. This is going to arrive here at, say, 10.1. And this other one is going to arrive at, okay? So I'm claiming that a bona fide clock, if this clock comes from here to here and measures this one, if for bona fide clocks, in such a way that
Sure, but this is only true if they both follow geodesic within P1 and P2.
what?
This is only true if they both follow geodesics between P1 and P2.
No,
Yes.
no, because they are arbitrarily close. And this is a very crucial fact. If they are arbitrarily close to each other, as you said, arbitrarily close, as you said, they only measure the size of the
Yes, but the
right.
size.
And what happens is that if they are arbitrarily close, this may be a geodesic, this may not be a geodesic, but if they are arbitrarily close, this size is the same of this size.
Sorry, close means close in space or close in time or close in both?
In space-time.
In both,
So,
space and time.
Yeah, so they are...
So they're at the same
I mean,
point in space-time.
there is always a neighborhood in your manifold in such a way this must be true.
Sorry, they're at the same point
Look,
in space-time.
it doesn't matter what this something is accelerated or not. What? No, if this is arbitrarily close, they don't matter.
Okay. You are discarding quadratic pieces. Okay.
Arbitrarily close means zero.
No, arbitrarily close is arbitrarily close. It's not zero. I don't know what arbitrarily close means. Okay, this is arbitrarily close.
Thank you.
What I'm saying just is that this distance is going to be that, and this does not depend whether the clocks are accelerated or not. It only depends on what are the events, here and here. This is space-time, here are the events. It doesn't matter for the time interval that this clock is going to measure whether the clock is accelerated or not. Yeah.
I mean, I'm assuming that you think that this is an experiment that can be done. Therefore, my question is, it depends on the unit of times
No, it
of
doesn't.
both clocks? I mean, imagine that the frequency that determines how the clock ticks they are both atomic and they are from different atoms with different frequencies. So, I mean, that's what I'm trying to say. Is the unit of time the same in both clocks?
Well, if one clock measures in seconds and the other in minutes, then you have to convert one unit to the other, if this is what you mean. But of course, they are identical bona fide clocks. You can think of these bona fide clocks produced by the same factory, and they are in principle identical. But the problem is, how can you be sure that they are not cheating in a smart way, in such a way that they begin making ticky-tack, 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 and then they stay in a smart way, making ticky-tack, ticky-tack, and so on and so forth. These are not bona fide clocks, and these are going to be ruled out by this procedure that I gave you. These ones are not going to satisfy this condition, Any other question? Okay. Okay, the problem, not the problem still. The fact is that bona fide clocks must be, according to the theory, in order to satisfy the previous condition, clocks must be point-like and have a classical word line. Why? Because events are point-like, and in order to make sure that they visit both events, you have to have a classical word line. Because if they are not localized, you are not sure whether or not these clocks did visit P1 and P2. Okay, this is what the theory asks you in order to define a relativistic spacetime. By relativistic spacetimes, you should think of a smooth manifold endowed with metric. This metric is precisely the mathematical quantity that is used to reflect what bona fide clocks measure. Good. Now, this is what theory asks you. Something different is what nature can provide you. And we know that nature cannot provide you with point-like clocks. And so the best realization that nature allows us for these idealized bona fide clocks are small clocks circumscribed by a classical container in order to make sense of what is a classical word line. And because these are small clocks, it had better that we consider the clockwork mechanism as a dynamical system ruled by quantum mechanics. So the best realization we have for a bona fide clock, for example, an atomic clock, has a classical container, and but the dynamical system describing of the clockwork is quantum. Okay, but this has consequences. Okay, the fact that we don't have this idealized all the way apparatus needed to define a classical space, a relativistic space-time, this has consequences. What are them? The question is, that I would like to ask you, and I'm going to answer in this seminar, is, are there bona fide clocks able to measure space and time intervals of Planck size? And the answer is no. Let me illustrate it, trying to measure, telling you that we are going to measure let's say, how we can measure this ruler. Okay, I need two ingredients, one from general relativity and one from quantum mechanics that I'm assuming. Let me state what are these assumptions. So according to general relativity, and this is standard general relativity, very, very basic general relativity, every massive object, yeah, maybe you want to make your question before I proceed.
Yes. So when you write that formula, ds squared equal to g mu nu dx mu dx nu.
This?
Yeah.
Yeah.
So let's say we are in two-dimensional special relativity. Okay. So this will be like ds squared equal to dx squared minus c dt squared.
I'm sorry. My English is really poor, okay. So you have to repeat it slowly.
So, delta s squared will be equal to delta x squared, the space, minus c delta t squared, right? That interval.
Look, this is if you, okay, let me just write down this.
Yes.
You are in special relativity.
Yes.
This is true for any coordinate system.
Yes, agreed.
But now you are choosing a Cartesian coordinate system that usually we represent like this.
Yes.
And by definition, if you are using Cartesian coordinate system, this quantity
yes.
Okay, just before you continue, just one observation. This is not time, this is not space, these are only coordinates that are used to map that.
Yes,
okay.
So my question is, according to, if I understand you correctly, all these dt, dx, dy, and dz, all of this can be measured in terms of some clock. The
can
clock
be what?
Can be measured using the clock that you are describing.
Can be measured.
By using the clock that you are describing.
Yeah, well, actually, we should not think like
independent.
This. You should not think like this. Let me rephrase what we are saying in the following way. Take one event, say here, P2. Take the other event here, P1.
Yes.
ds squared between P1 and P2
will be
in these coordinates are going to be given by that.
Yes, and another coordinate, yes.
And if they are arbitrarily close, what your bona fide clock is going to measure is this size, which does not depend, this size, which does not depend whether it's whether or not it's inertial, because they are arbitrarily close. And as you see here, it only depends on what is dt. This is P1. T1, X1, blah, blah, blah. T2, X2, blah, blah, blah. You just put it here. This is ds squared. This is what a bona fide clock is going to measure.
Yeah, yeah. So that's what my, I was trying to infer that this bona fide clock will measure all the small, I mean, the time coordinate, the space coordinates.
No,
Okay.
because of the following.
Okay.
You cannot have a clock going, clocks only, this must be causally connected, meaning that these two events are not causally connected, so you're not measuring in this way this distance. In order to measure this distance, you need 3 clocks, as I showed you before.
Okay, so 3 different clocks will be.
Yeah.
Okay, fine. Yeah, thanks.
Any other question? Good. Okay, so let's take this body here. So this body, according to general relativity, has a Schwarzschild radius. If I make G equal to 1 and C equal to 1, the Schwarzschild radius is given just twice the clock mass. Sorry, this body here, twice. Okay? If this quantity here is smaller, if twice the mass, the Schwarzschild radius, is smaller than this body, that's fine. Nothing happens in principle. But if twice the mass of this body is larger than this body, you can circumscribe this body by a circle, by a sphere, with twice, with this radius, then this is going to collapse into a black hole. Fine? Okay. So of course, the Schwarzschild radius of this is smaller than this size, because otherwise this would collapse into a black hole. Okay. So let's write down the Schwarzschild radius of our clock. It's twice the mass of the clock. Of course, this must be smaller than the size of the clock, otherwise our clock would collapse into a black hole. Now, the mass of the clock is larger than the mass of the clockwork mechanism, because this has also the container. Now I'm using quantum mechanics here, next step. According to basic quantum mechanics, if you want a quantum clock, to have a precision delta t, it must have an energy larger than h bar over delta t. Okay, this is theory of quantum mechanics for quantum clocks. And this does not depend on the realization of your clock. Now, let's assume, now I'm going to use this inequality, that if you want to measure a distance of 1 second, the tick-tack of your clock must be smaller, the precision of the tick-tack of your clock must be smaller than 1 second light. If you want to measure 1 second light, the tick-tack of your clock has to have a precision better than 1 second, meaning that if you want to measure the distance between Earth and the moon, that's about 1 second light, your clock must have a precision better than 1 second. Otherwise, you don't measure anything. Using this inequality here, you have that this quantity is larger than h bar over the size of the object you want to measure. Okay, next step is just rewriting the Planck size in terms of h bar, assuming that g equal to c equal to 1, because they are conversion factors in the relativistic spacetimes. C is not a conversion factor in Galilean spacetime because of what you said. Now let's assume that I want to measure a distance smaller than the Planck length. Okay, this is an assumption. Let's assume that this is smaller than the Planck length. If this is smaller than the Planck length, this thing is larger than the Planck length. And as in the last step, I use again this to write that. And L must be larger than the clock. Why L must be larger than the clock? Because if you want to measure the distance between the Earth and the moon, your clock has to be smaller than this distance. Using this last step, you end up that the Schwarzschild radius is larger than your clock if you want to measure a distance smaller than the Planck length. If you want to measure a distance smaller than the Planck length, and you believe in basic quantum mechanics and basic relativity, your clock must be so heavy and small that this would collapse into a black hole. The same is true if I repeat this argument to measure time intervals smaller than the Planck length. This means that, as I told you, to measure distances, time and space distances at the Planck scale, clocks should be so small and heavy that they would collapse into black holes. So, and this is a very important point, it's not reasonable to trust that space-times, as we understand them today, smooth manifolds endowed with metrics, should be trusted at the Planck scale, just because you don't have bona fide clocks, neither to define them nor to test them. You cannot test, you don't have bona fide clocks to test those distances, as I tried to convince you before. So that's fine. I think this is a very strong case that what we relativists understand by spacetimes as manifolds, smooth manifolds endowed with metric, is fine, but an effective model as far as you don't probe distances at the Planck scale. So this is a very important message here. If you wanna, okay. Now, yeah, you have a question.
Can't you actually take the other side of the conundrum? Can't you just use these all demonstration and come to the conclusion that bona fide clocks do not exist?
If bona fide clocks does not exist, then spacetimes, relativistic spacetimes, are not well defined. Well, relativistic spacetimes, that's mandatory in order to define, because in order to define them, you have to give an opportunity to test them, that bona fide clocks exist. If bona fide clocks don't exist, you have to change
all of relativity.
Everything, yeah.
Okay.
Okay, so if you agree with that, the manifesto, and this closes the first part of the seminar, says that laws reliant on space and time parameters that are at the Planck scale or beyond the Planck scale are not reliable, just because the space-time on which they are defined is not reliable. As we understand these days, physics, we first define the space-time, and after that, we define the Hamiltonian, whether relativistic or not, or non-relativistic. So beforehand, you have to define in what space-time you're going to work. Except maybe loop quantum gravity is not like that, but I don't know anything about loop quantum gravity. Okay, so this has consequences. The consequence is that wave mechanics should be amended for particles with masses larger than the Planck mass, just because the first step in order to define quantum field theory or quantum mechanics or wave mechanics for particles with masses larger than the Planck mass is to believe in one-particle wave equations. And one-particle wave equations depend on just one parameter, namely the Compton length. And the Compton length for masses larger than the Planck mass is smaller than the Planck length. So there is no reason to believe in an equation that depends on a scale where the space-time on which this is defined is not trustable. There is no reason to believe in equations that depend on parameters that cannot be defined in some space-time. Okay, so what's our proposal? Our proposal is to change our mindset about quantum mechanics in the following way. As we see these days, quantum mechanics, at least people as I use it to see, I use it to see that, as I said in the beginning, that quantum mechanics is defined on a classical space-time, and because these things are made of quantum blocks, eventually this classical mechanics would be an effective theory emerging from quantum mechanics defined in a classical spacetime. So the proposal is that what's fundamental is some unknown, uncharged quantum spacetime. We don't know anything about quantum spacetimes. This is the fundamental theory where you could probe the Planck scale. We could probe the Planck scale. We don't know anything about that. Then, from this uncharged, unknown theory, quantum space-time, that would be valid, that we don't know anything, but who describes physics at Planck at distances smaller than the Planck size. This is distances here are smaller than the Planck size. Would emerge two very good theories, very well tested in nature: quantum mechanics and classical mechanics. For distances that are very well tested at distances much larger than the Planck length. But because what I told you before, the quantum mechanics would be good to describe this left-hand side, namely particles with masses smaller than the Planck mass, while this other equal emerging theory from this uncharged unknown theory, classical mechanics, would describe particles with masses larger than the Planck mass. And this is, at least this is in agreement with experiment. Now, the problem is that these two theories, very well-tested theories, in their respective domains, are separated by a Heisenberg cut about at the Planck mass. So this ridge emerging from this, as a tectonic plate from this uncharged underlying unknown theory would separate these two domains. The question is, what kind of new physics should we expect when we treat particles with masses larger and larger and they get closer to the Planck mass? Because this is completely new physics, and as we approach this region from the left, quantum mechanics should experience some modification.
So do you distinguish fundamental particles from composite particles? When you say mass, you mean it could be some bound state of thousands of atoms?
It can be, So by here, I am assuming here a system, here, for example, take here. In order to test it, the idea is to test with composite systems. But when I say mass, I'm talking about the mass of the center of mass of the system. I'm going to discuss this later, okay? But that's a good question in the sense that when I'm talking about mass, I'm talking about the mass of the center of mass, of the system as a whole, okay? If I'm talking, say, about protons, I'm talking about the mass of the proton and not of the quarks, and so on and so forth. Okay. So what do we need? So this is the first part of the seminar. Now I'm going to try to realize what's the new physics that we are going to experience as we analyze free particles, free systems, if you want, free systems, right? You may have internal interactions, but the system as a whole must be free. What?
Mean for a system to be free if it has interactions?
What? Sorry, again.
Internal interactions, what does it mean to be free? I don't know what you mean by free.
Look, if, for example, I have, this has many interactions here. If I throw it to the universe, right? So you can describe the center of mass independently of the internal degrees of freedom. And this is going to be free if you don't have external agents, this is, say, in the cosmic, no espaço sideral, whatever, in the free space. So this is, what I mean is that, well, I don't know if you got it.
I think I understand what you're saying. You're saying it's a closed system.
Internal interactions then does not affect the center of mass of the system if this is in free space. Okay. Internal interactions does not affect the center of mass of a system if this is in free space. If this is not in free space, it would depend on the potential. If the potential is, say, linear, you can decouple the center of mass from the internal degrees of freedom. If it's not in a linear potential, you can't. This is why you have tide effects, and why you don't see one face of the moon, and so on and so forth. But I am assuming that our system is free in free space. Free, meaning that you don't have external influences acting on your system. Say, a crystal in free space. The crystal has internal degrees of freedom. It has internal interactions. It doesn't matter. Okay, this is what people indeed are trying to do with levitation experiments. They try to levitate crystals, and so this is very standard. Yeah?
Okay, that's right. So when you say that some cluster of particles is free and moving in space-time, you mean that it follows a geodesic through space-time?
Yeah.
Right? But if it has internal degrees of freedom or internal interactions, or it can get very energetic, and as it gets very energetic.
What do you mean by you don't get very energetic? What do you mean by that?
You might get very energetic.
What? The center of mass?
No, your
energy is always a concept depends on a observer, right? As you know.
Oh, yes,
so when you say that this is very energetic, what do you mean? What are you measuring, and who is measuring that?
I mean, as you increase the mass of this bunch of particles, you start to have back reaction effects with space-time, doesn't it? How do you even define a geodesic in this case?
Well, I'm assuming here that, here we are trying, we are analyzing a situation where the background space-time is not that energetic that you have to take into account back reaction. So I'm analyzing, say, what happens with the physics when I take a crystal of 10 to minus 5 grams, meaning, and the physics will change, as we will see, because you approach this Planck mass, but this is not going to affect the space-time in any important way. So the problem you are pointing out is very important, is the problem of back reaction in quantum gravity. I don't have anything to say about that, too complicated. But we, Gabriel and I, only want to see what kind of different quantum mechanics laboratory effects you are going to get if you test particles, say crystals with 10 to minus 5 grams. Okay? Okay, so the theory, first of all, must respect experiments. Free particles with small masses must obey quantum mechanics. Free particles with large masses must obey classical mechanics. Quantum particles must self-decohere as mass approaches the Planck mass, because we would like that a complete, comprehensive theory shows how you move from quantum mechanics to classical mechanics, where you cannot put in superposition massive particles. The model must be gravity-oriented, because, as I told you, my only argument is based on space-time, and space-time for relativists is gravity. And the model must respect Lorentz invariance, meaning that whatever you get for this system, in one reference frame, the same is going to be true in any other inertial reference frame. So we have to satisfy relativity. Okay, so I'm going to give you the simplest possible realization for the model. If you want more details, please visit our paper. But because I want to make it simple, let us consider the simplest situation where I can think of explaining our model. So first of all, we assume that, if you want more details, please go to the paper. We assume that the center of mass, degrees of freedom, don't you agree with everything because you are laughing, I think? You are laughing because you're delighted with that or because you don't agree with something? Okay. So we assume that the center of mass is decoupled, so we are going to only to look at the degrees of freedom of the center of mass, because these degrees of freedom are assumed to be decoupled from the internal ones. Okay? Okay, so if this is so, we are going to treat complex systems as crystals, as a particle. A composite particle, as protons are, but a particle. Let's assume this is free. If this is free, a particle satisfies the Schrödinger equation. Again, now, we are not using Schrödinger equation because we are assuming we are in a non-relativistic space-time. We are assuming that we are in a relativistic space-time, but because we are sitting on the center of mass of the system, we can make calculations using non-relativistic space-times, and this is without loss of generality. Not because we are assuming non-relativistic space-time, just because making non-relativistic calculation gives the same results as if I were making the calculation assuming the Dirac equation, say. Okay, so let's consider the Schrödinger equation, and let's consider an initial state given by a Gaussian. Now, according to our model, we must duplicate the system with a clone. Yeah, go ahead.
Just to make sure I understood your last point, you're saying that you're doing physics in a region of space-time that's sufficiently small compared to the typical characteristic time scale of curvature, so you can neglect general relativistic effects.
Yeah,
okay.
Right.
Thank you.
And also, the internal parts of the system doesn't move fast enough. You know, the internal constituents of the system has small velocities with respect to the frame that sits at the center of mass.
So you're also going to neglect special relativistic effects.
What? Otherwise, we would have special relativistic effects. Okay. Right. But because I am treating, you know, the system only the center of mass, it's okay. Okay, so we must clone the system. And this clone, just take into account that this clone is not physical, it's just a mathematical artifact in order to make physical predictions. You can think of it as we think of wave functions. Wave functions are not physical, although it allows us to make predictions that can be confirmed in the laboratory. So the spirit is the same. Okay, now we couple both things, both particle and clone, using a gravitational potential that only differs from Newton's gravitational potential because we have this Planck scale here that avoids distances to be smaller than the Planck length, because as I told you, we don't believe in relativistic spacetimes at scales smaller than the Planck length. Okay, so the initial state that we assume is just this one. They are pure state, right? Clone and particle, and then quantum mechanics follows. Why? Just the observation. Because we are falling to this direction from the quantum mechanical domain. So we are going to use quantum mechanics. Okay, using quantum mechanics, you can evolve it in time. And then, because the clone are not physical, you must eventually, this is the protocol of our model, trace over the degrees of freedom of the clone. And you end up with the density matrix for the particle, which is mixed because part of information flows from the particle to the clone. This is standard quantum mechanics. The question is, what are the consequences to the particle because of this coupling? And now I jump directly to the results. from this density matrix, you can calculate the purity, and the purity says, basically, for those who are not in quantum mechanics, how much of the coherence of the original particle is lost to the clone, right? So assuming quantum mechanics all the way, the evolution is unitary, and then you begin with a pure state, and you end up with a pure state. But in this case, you have this clone stealing coherence from your particle, meaning that eventually the final state is not expected to be pure, it's going to be mixed, meaning that the purity is not going to be 1, because if it were 1, then no coherence would be lost to the clone. This is the time evolution of the purity, so it begins a pure state, but as time evolves, the purity of the system drops because, as I told you, part of the coherence of the particle is lost to the clone. And these are the final purities that you find for a particle with mass. We took here, assumed a mass that's half of the Planck mass. Here you have the final purity for different masses, half of the Planck mass and Planck mass for different dispersions of the Gaussian. You see that it's not sensitive to the dispersion of the Gaussian. But what we can see here is that the larger the mass, the smaller the final purity. This is in agreement with the fact that we expect that the larger the mass, the more the system is going to look like a classical system.
George,
Yeah.
you effectively, at least from my point of view, you're putting in a cutoff, this LP squared, but that cutoff is not Lorentz invariant. So
Sorry, again,
you're putting in a cutoff. That's how I view this LP squared. But that cutoff is not Lorentz invariant. So I thought you were going to assume that Lorentz invariance was preserved.
Yeah. The calculation is made in the rest frame of your system. Okay? So by Lorentz invariant means the following. You cannot, by any experiment, privilege one inertial frame from some other inertial frame. Because this protocol is always made with respect to the center of mass, it doesn't matter whether the system is here, forgetting the existence of Earth and so on and so forth, or in some other frame. The calculation the protocol is prepared only to be applied in the rest frame. And this is Lorentz invariant because no matter how is this crystal flying, the result is going to be the same because the calculation is always made with respect to the center of mass. So there is no underlying environment, as in Caldera-Leggett, say, where Caldera-Leggett has a privileged environment where that defines a privileged frame. We don't have it here. Is as this environment was always carried with the particle. Yeah.
Maybe if I can try to reformulate the question in a different way, is there a way you could propose a covariant formulation of your thought experiment in such a way that we would see that it doesn't matter that you are indeed choosing to do your calculation in the center of mass using non-relativistic formula?
Okay, so we are saying how can we rephrase this theory in a way that it would be valid in any frame, right? We didn't think of it yet. Okay, but let me make sure that you agree with me that the protocol does not privilege any reference frame because it doesn't matter whether the crystal is flying there or here, the calculation is always taken with respect to the center of mass. So this time that I'm putting here is always the proper time with respect to the frame that flies with the crystal. Okay? Go ahead.
No, my question is much simpler. What are the error bars? If you tell me to just go and read the paper, it's fine, but do you know what are the error bars?
Yeah, so the error bars is the bars given by Mathematica when we try to make this calculation. So more details with Gabriel Aguiar. Okay? Okay, here you see the error bars are smaller. Okay, I don't have time to go into details, but let me say that our model can also be tested in a Stern-Gerlach experiment. And we are in conversations with experimental groups that are making levitation of crystals, of silica crystals, right? In order to see how feasible is a test of this model. So let me go to my final conclusions. The first conclusion, well, as I hope the idea is to convince you that you're not going able to put massive things like this one in superposition, even if you, there is an intrinsic impossibility of putting massive systems with masses larger than the Planck mass in position superposition. So we are not going to have Nathan here and there, thanks God, at the same time. So don't try to make don't try to make double slit experiments with cats, because you are only going to kill your cat. Despite it, although our model does prohibit systems with large masses from being in spatial superposition, it does not prohibit, for example, crystals with large masses, large crystals, from hosting superpositions of phonons. Why? Well, first, because of many reasons, but let me just list two of them. First of all, phonons are massless. And even if you are worried about the energy of these phonons, they are much smaller than the Planck energy. So there is no problem about having crystals, massive crystals, that are not going to be, that are not, you are not going to put them in superposition, and despite it, allowing them to host quantum phonons. In particular, applying this to black holes, from our view, from the view given by this model, black holes are going to be intrinsically classical systems, because black holes in general relativity are massive systems with masses larger than the Planck mass, because otherwise, for black holes with masses smaller than the Planck mass would have a Compton wavelength larger than the radius, and it would be like a black hole would leak outside itself. That's not what we understand by a black hole. So black holes must have masses larger than the Planck mass. And because of our model, this means that they would be classical. Don't try to put in superposition a black hole here and there. But despite it, spin 2 massless particles that we understand as being gravitons, being emitted by fluctuations of these black holes, there is no reason why they cannot be quantized. There is no reason why classical black holes could not emit quantum gravitons. So in summary, quantum mechanics would apply to particles with masses much smaller than the Planck mass, classical mechanics to particles with masses much larger than the Planck mass. There will be no measurement problem, because, making a long story short, the measurement problem is how can a apparatus collapse the wave function if we treat it as a quantum system, knowing that quantum systems evolve in a unitary way. To collapse means lose information, but if the apparatuses are quantum things, and everything are quantum things, then there is no loss of coherence, because the whole thing is unitarily evolved. In this case, there is no such a problem, because the apparatuses are here, they are classical, and they are the things that are the apparatuses that will collapse quantum systems. Also, there is no meaning about wave function of the universe that some people talk of, no stress. So, just to finish, I would say that I subscribe almost 100% from Bohr's view. According to Peterson, in his Bulletin of Atomic Scientists, he says that Bohr believed that there is no a quantum world. There is only an abstract quantum physical description. It's wrong to think, according to him, that the task of physics is to find out how nature is. Physics concerns what we can say about nature. I subscribe almost everything, but the end. Physics does not concern about what we can say about nature. Let me rephrase it by saying that physics concerns predictions of measurements. We don't say anything about what nature is. This interpretation is a human thing. We only make predictions about numbers. About what we can say about nature, from these predictions, well, whatever floats your boat. Fica a gosto do freguês. Okay? So, thank you very much.
Thank you, George. Very nice colloquium. More questions?
Well, thanks for the talk. It was excellent. So I have a question that is the having like a clock that measures very small time scales just a restriction on relativistic spacetimes, or is it can be applied to any theory that has a like smooth manifold structure?
I would say that because all the argument is based only on general relativity, the existence of black holes in general relativity, and quantum mechanics, basic quantum mechanics, this rules out most. Well, this would not rule out a metric description of space-time if it doesn't contain black holes, for example. But we know that Sturani left it, but we know that this is a well-established thing, that there are black holes. So I would like, so that's, I think, all I can say by now.
Okay. Can I ask like one more quick question? So you find that the coherence of the system that is gravitationally coupled, it disappears, but where it went for? Like
to the clone. And the clone plays the role of this quantum space-time degrees of freedom that we don't know. So this is an effective description where particles like this, if you try to put this in superposition, you are not able to, because when you try it, immediately, because the mass is large, immediately any coherence flows very effectively for this quantum space-time degrees of freedom, that we don't know what they are. This is why we don't have a fundamental theory. This is an effective theory, but the idea would be this one. This is an important point. So did you understand my answer?
Yeah, I got to think on that, yeah.
Okay, so coherence of the particle, a physical particle, flows to quantum space-time degree, should flow, according to our view, should flow to degrees of freedom of a quantum space-time in a very effective way if the mass is large, but if the mass is, a elementary particle mass, then we can also show that it doesn't lose, basically, it doesn't lose any coherence to these quantum degrees of freedom. So the model, in this sense, is coherent because quantum particles keep their coherence, and they are very well described by quantum mechanics, while only very massive systems lose coherence to these degrees of freedom that we don't know yet.
Okay, thanks.
Thanks for the talk. Can you also approach from the right side?
No.
No.
And the answer is the following. So this reach is given by the Planck mass, and the Planck mass, if you make, take out all these conversion factors, is given by h bar, and you don't have h bar in classical mechanics.
Up here.
Yeah.
So I want to understand a little bit better, I think it's related to his question, the measurement problem that you say is not non-existent here, right? But if you think take a very simple measurement, right? Like a photon going to a photomultiplier, right? At any point in time, once the photon goes in, right, it's only interacting at single particles, right? So you still have to solve how you transition from these interactions, right, which all of them are unitary, and you're just entangling the photon with more and more photons, right?
Yeah.
To the point where you go above this threshold, right? And then, if I understood your answer to him correctly, once you have a number of particles big enough that are all coherently entangled with the initial photon,
No.
then this flows out to these...
No. Look, it doesn't have to do with large number of particles.
Well, the total mass, I mean, right? I'm using the number of particles, but eventually you get above a threshold in mass.
So can you repeat? So are you making a double slit experiment with single?
No, just think a photon going into a photon multiplier, right?
Okay.
And I'm looking, say, for the polarization of this photon. It's some measurement that I can know the polarization, right? So I have to collapse the spin wave function of this photon, right? But at any interaction, if I follow the photon around, right, it's only ever interacting with single particles, right? It's a photon hitting an electron that emit more photons and hit more electrons, right? At every point, you have quantum mechanics, right? And there's this transition from microscopic to macroscopic. That's where finally there's a collapse, right? And there's still the measurement problem there, right? You know that the big system, right, the whole detector, cannot be quantum from your argument, but you still have this, if you follow the progression of the photon, right, you only ever see quantum mechanics and more quantum mechanics, right? And you never have a collapse anywhere.
Okay, so let's, I think there are many formulations of the measurement problem. I'm giving you the simplest one. In the simplest one, you have to have something that collapses the wave function. And according to the Copenhagen description, in principle, you would not have, because, well, sorry, not the Copenhagen, about this deep thinking of quantum mechanics, that everything is quantum. Everything would evolve unitarily, and if you evolve unitarily, you don't have how to collapse, and people try to solve it with environmental decoherence, which does not really solve the problem, but pushes the problem to some other domain, I would say. Okay, so you went into the details of the apparatus. You went into the detail of the apparatus that I prefer not to enter into the details, okay? Probably because I'm not sure enough. But look, that my initial formulation of the quantum of the measurement problem does not exist, because you can't separate what's the domain where apparatuses live versus quantum mechanical systems. Now you can think of the following. Well, how can we couple quantum systems with classical systems, which is a kind of what we are saying. But we know this is an effective theory, and we know from effective theories that you can, for example, wonder how classical currents couple to quantum systems, right? So this is what we expect, where this is the classical, just inverting it, rather than wondering how a quantum charge influences a quantum system. here we are saying that a quantum system can influence a classical system. But the apparatus is here, and this is, in other words, you would not have an apparatus with a mass in your laboratory with a mass smaller than the Planck mass.
Okay, so
this is at least a necessary condition, maybe not sufficient.
Okay, but you agree that the measure problem is still into figuring out that interaction, right? It's still there.
Yeah.
Okay.
Yeah.
Okay.
Yeah, I agree that I am only saying that at least we have put a boundary where apparatuses would live. They would live in the classical section of that graph. Only that.
Okay,
only
very quick, maybe simple one. These quantum degrees of freedom, right? As you said, well, the coherence is...
Quantum space-time degrees of freedom.
Yeah, the quantum space-time. Does that avoid hidden variables, Bell's inequalities, or...
No, because Bell inequalities and all these are tested for quantum systems, and for quantum systems, we have shown in our model that this model is very, very inefficient to steal coherence from the system. Right? So what I'm saying that all quantum mechanics we have tested so far is in this region. People are struggling in order to approach this region here. And we are very far. I don't think I'm not optimistic that I'm going to see an experiment testing this model in my lifetime, because we are in this region here. Okay? People are struggling in Austria, in Israel, and even at Universidade Federal Fluminense. They are doing their best, but it's not really easy to do it.
One last question.
Yeah.
So your idea was, it's kind of suggestive of maybe some other proposal by Roger Penrose of gravitationally induced decoherence. I don't know if there's a connection between the two.
Yeah, Roger Penrose has criticisms about quantum mechanics, and he tries to make a gravitational decoherence, self-decoherence also, but this is completely different from this proposal, because according to him, there are spontaneous collapses of the wave function, but between one moment and the next collapse, the system would follow a wave mechanics. The more massive the system, or the larger the superposition, the faster this spontaneous decoherence, spontaneous collapse. According to our model, if the mass is larger than the Planck mass, you are not going to allow the evolution of massive bodies by any wave equation. There's no wave equation that would evolve this. So this proposal is quite original, I think, in the literature.
Okay, let's thank George again for the discussion and the colloquium.